The goal of this project is to control a two-link robot in an unstable state as an inverted pendulum. We began this process by familiarizing ourselves with the robot. The robot has two rotary links with an encoder on each link. Link 1, the link closest to the base, has a motor. In addition to the real system, the robot was simulated in Simulink.
In order to calibrate the real system with the simulated system, we found the theta parameters required for system identification. This was accomplished first through manipulating the dynamic equations to find the theoretical theta parameters. We then used our Hamiltonian to find the theta parameters of our real system.
Since we want the robot to behave differently depending on the position of link 2, we section the robot into 3 states. State 1, at the bottom of the pendulum, is responsible for the swing up. State 2, on the sides of the robot, is an in-between state, and state 3, at the top of the pendulum, is the balancing state.
Section 1 is responsible for the swing up. The position of Q1 is approximately equal to portions of the position and velocity of link 2. This subsystem shows the influences of Q2 and Q2 dot on the desired Q1 position. In a separate subsystem, we put our Q1 position controller. In order to ensure that our system is responding quickly and efficiently, we designed a controller with 5% overshoot and the time to peak as 0.15 seconds. We solved the transfer function for the subsystem and compared this with the characteristic equation and found Kp and Kv values. For state 1, we need to alter the reading of Q2, so no matter which direction the pendulum falls from state 3, the position controller will be able to read the correct quadrant. Using the function atan2, we were able to determine the quadrant of Q2. The corrected Q2 value is now the input to find the desired position for Q1. As we see from the Simulink, the new Q1 desired is inputted in the position controller, which finally outputs a voltage.
After finishing the swing up, we began working on state 3, the balance state. In state 3, we had a discontinuity at 0 degrees. In order to use this state, we had to linearize the system around the point at 0 degrees. We first needed to alter Q2 again using the same atan2 technique used in the previous subsystem. In order to linearize the system about the equilibrium point of 0, we need to use the Jacobian. This is done by taking the partial derivative with respect to f, the matrix of accelerations. The A matrix is found by taking the Jacobian with respect to state variables, and the B matrix was found by taking the Jacobian with respect to the inputs and plugging in the equilibrium point, which produces the A and B matrices we will use to find the eigenvalues. Since one of the eigenvalues found from this system is positive, the system is unstable. In order to stabilize the system, we must place poles at -5, -5.1, -5.2, and -5.3. We also know that U equals -kx due to state feedback. In order to implement this into our system, the K matrix was then inserted into our Simulink by a gain block using the matrix multiplication, and the state variables were then inputted. After implementing this part into our state 3 controller, the system successfully balanced and matches our simulated system.
After this, we worked on different types of position control when in state 3 using state feedback.